We're going to talk about the project Federated Named Entity Recognition, and we can start by introducing yourselves. So my name is Lovisa.
I'm Jennifer. I'm Katriin.
I'm Thibault.
And you are all from different universities? Or?
Charles.
So now you have us. So the problem we focused on was that we have the Santa Association, and they need to develop a really accurate naughty list, which requires comprehensive surveillance. Surveillance over text, surveillance from text, which is very excruciating to do manually. So currently we have the teddy bear on the Santa Association. He's really mad because he's so tired of reading all of these texts all the time. We also have this issue that the Santa Association, like, while they like to collaborate, they don't like to collaborate too much. So they have their kind of collected data sets, but they don't really want to share it with each other. They kind of want to keep it to themselves. And also they have quite little data. So while they feel like it would be nice to leverage our combined sources, we don't really want to give you our Norwegian data to misreach people. So yeah, this is a made-up scenario to motivate a problem. The solution that we focus on for this problem is, first of all, to use named entity recognition, which is based on NLP. So it's like automated detection of named entities. So there we have the little robot replacing the teddy bear. What we also do is, since people don't want to share their data sets, we use federated learning to be able to actually share the data. So this is what we're focusing on, and we will go through these different parts in our setup throughout the presentation. And I will start by quickly talking about named entity recognition a bit more, so the kind of task that our small robot has to solve in a federated manner. So it's essentially about detecting these entities. So it's like token classification. And you saw the first example here, where en taget professor i statsvetenskap vid Universitetet i Oslo och faststudien på dagtid. So I don't really know Norwegian, but that's what it is. And there you have the person, the organization in blue, and then the product in green. And for simplicity, we also included an English sample, even though our data set is completely in the Nordic languages. So here, for example, you have that Apple announced their new iCase. And here, for example, Apple, I mean, you both know the fruit apple, but here from the context, it's quite clear that it's that company, so the organization, which is why it should be marked as a named entity. And you can maybe also see here why it's a kind of tricky task to solve, and that your NLP systems need to kind of learn. Moreover, maybe you have new entities. I don't think there's anything called iCase yet, but if it appears in this kind of context, maybe you want to assume that this is some kind of product. And here you have a comparison then where you actually don't have any entities. And this is also something that the model kind of needs to learn. And that's what named entity recognition is really about. And usually what you use is transformer models. So purely text transformer models. And typically the encoder part of a transformer model, which is also, so you use CLIP, which kind of also leverages encoders to some extent. So you essentially train these types of models to detect named entities in some language. So that was it about named entity recognition and the first setup. And I think we're moving over to the federated database.
Model together, they don't want their own data. And since they're going to share their own data, we don't have any assumption on what, like, how that data is distributed, right? So, for instance, here, like, each federation has data in their own language, and they have possibly like different content. We're gonna check that. And to solve this problem, we use federated learning. So what it means is that we create a model in the center as a global model or our named entity recognition task. And then each client, each federation, will actually work with their own data locally to train their own model. And then they will communicate the new weight they get when they train their local model to the global model. And then everyone does that independently, and basically you repeat that, and there we go. But that's the theory, but we live in a real world with like real things. So in order to perform this in real life, we need like to take care of like a few practicalities. So we need data sets and a model and a machine to deploy implementation and a framework to simulate communication. So we'll go through that and like what were the choices we made in that context. So first for the data set, we chose to work with the UNER dataset, which is a unified dataset corpora for name entity recognition tasks. It's a very recent project. I think it came out this year actually, and it comes from it builds upon a corpora already existing corpora from universal dependencies, which is a very high quality dataset with annotation on text, and it has a layer of name entity recognition tags. The specificity compared to the setup we had before is that we only have 3 types of tags: person, organization, and location. And it's a very nice dataset to work with because they spend a lot of time in solving dataset ambiguity. So before we had an example with like ambiguous case, maybe with Apple, and that happens a lot, and it's a real problem in the recognition. And there was a lot of effort put to have like consistency labeling guidelines, so which helps a lot. And also there are a variety of datasets to have the heterogeneous setting that is common to federated learning. So we chose 4 datasets, 1 for Swedish language, 1 for Danish language, and 2 for Norwegian language for the 2 commonly official writing.
Written language?
Bokmål and Nynorsk. And yeah, and each dataset has different content and different sizes. Yes, and for our base model, we chose to go with Facebook's XLM Roberta as a pre-trained model. So it's a transfer-based language model that has been pre-trained on 100 different languages. And this model comes with like 2 very nice features. So the first one is that it's a multilingual model, so it can work with a lot of different languages, but it doesn't sacrifice on per language performance, which means that it will perform as good as a specialist model on a specific language. So that's very nice. And it can also, it's very practical because it can determine language on the inputs. So we don't need to specify what is the language we're feeding it. But we cannot use the base model just as is. It has a bit weak performances, so we do a bit of fine tuning. It's not the heart of like our problem, but it's still good to have a model that performs well. So we chose hyperparameters based on the one that were reported in the Meta or like Facebook research paper. And we added one bit more phase for training stabilization, and we performed early stopping based on validation loss. And as we will see a bit later, this enables us to have a good base model. Good, and yeah, and we are lucky to be able to deploy our model on Albis. So we applied and we managed to get access to it, which is a nice resource located in Chalmers. And we deployed our implementation on a small cluster, which consists of 4 NVIDIA A40 GPUs, and each client run separately on the GPU within the code. And now I will let Jennifer talk about how we use Flower.
Yes. Thank you. So I will introduce the framework we used for federated learning, which is the Flower framework. So Flower is an open source framework for federated learning. So you do distributed machine learning while ensuring data privacy using a number of clients. In our case, each client has been assigned a data set on that particular language. And one of the key promisings, if you will, of Flower is that it should be easy to go from this classical centralized machine learning setting to its federated counterpart. And one of the cornerstones for enabling this is that it's framework agnostic, so it builds on top of existing deep learning frameworks, and you're supposed to be able to use whatever framework you're currently working with. So it works seamlessly with, for example, PyTorch, TensorFlow, or many other frameworks. It's also compatible with Python, Android, iOS, C++, and there are many different examples with different languages, so you can often find an example for your application area to get going quickly. And from our experience, we were able to get going pretty quickly, so we can recommend it in that regard. And the aggregation in the server, for example, the aggregation strategy, the implementation is built on NumPy arrays, so it promises to be easy to combine with a lot of other development tools. The second cornerstone is that it's supposed to be scalable and flexible. So you should be able to move seamlessly from a sort of prototype setting to production mode. And to do this, Flower offers what they call a simulation mode. So here we can sort of emulate a truly federated setting on a single machine, or as we did on a compute cluster where each client works on its own GPU. And then Flower promises smooth transition to production mode with little to no code changes. So you're supposed to be able to do the entire pipeline from prototyping to launching an application on multiple devices or using a cloud provider. And then I want to talk a little bit about Flower's research branch. So it's not only focusing on applications and launching applications, but also on doing basic research in federated learning. So for example, one of the tools you can use is Flower's datasets. If you, for example, if you're doing research in federated learning and you develop your own application strategy, and you want to evaluate that across datasets of different domains. They have an interface for essentially, or a lot of Hugging Face datasets where you can use ready implementation of different partitioning strategies to get like a realistic or a good partitioning of these datasets across various domains. So there are a lot of things we didn't have time to explore in this project, but it seems to have promise in several areas of federated learning. So now we'll talk a little bit about the code structure when you're working in Flower with federated learning. So it's straightforward. You have the Flower server and the Flower clients. So the clients handles the local training based on the individual data partition. And then Flower is kind of a layer on top of your base model, which handles coordinating communication between the server and the clients. It handles combining the client model updates into the global model, so all the aggregation strategies, and orchestrating, in this case, for our projects, for example, the simulation mode. And the code structure is very simple. So you have 3 scripts, the server app, client app, and a script task.py, for example, which implements your base model. So here I illustrated this quite neatly, and the client app and the server app are 2 scripts that are quite small.
So I'm going to take out the results, but before I show you the result tables and our plots, I will quickly go over what you're going to see in the following slides. So we have 2 setups, a baseline setup and a federated learning setup. Because essentially what we wanted to know was, is it even beneficial to the federated learning, or would it be better to just train on the data sets I already have? So in the baseline setup, we were training and evaluating on a single data set, as you do, but we were also monitoring the validation loss on the other 3 data sets that we were not training on. Whereas in the federated learning setup, each client was training and evaluating on their own data set. So essentially, each GPU got one of the data sets and was training on that. And in the federated setup, we have 3 settings, which will be called S1, S2, and S3 in the following slides. In S1, we were only training on Danish and Swedish. In S2, we added one of the Norwegian datasets, and in S3, we were training on all 4 datasets. So, coming back to the baseline setup, we were training for 10 epochs. We limited the number of steps per epoch, and we used early stuffing. Why did we limit the number of steps per epoch? Because initially, when we were experimenting with federated learning, we noticed that 2 of the GPUs were sitting idle for long periods of time. And the reason is that the datasets have very different sizes. So the Norwegian datasets are about 4 times bigger than the other 2. And we didn't really want our jobs to get killed because we weren't efficiently using the GPU. So that's why we decided to limit the steps per epoch. In the federated setup, we are here now. We were doing 10 rounds. 1 epoch per round, and also limited the number of steps per epoch. At the end of each round, the global model gets updated, and then the next round starts from this updated global model. And that is the reason that we did 10 rounds with 1 epoch rather than doing 1 round with 10 epochs, which would better correspond to the baseline setup. We evaluated using precision, recall, and F1. And not to overwhelm you with numbers, we will not show you category-specific results. If you remember, we have these 3 categories: location, person, and organization. We will only show you aggregated results. So here are the baseline results. Don't worry, you don't have to memorize any of the numbers. I will tell you everything you need to know. But the interesting part is the plot on the right, where we were looking at the final validation loss on each dataset. So on the x-axis, you can see the training corpus, and on the y-axis, you can see the corpus we were validating on. And the numbers are the final validation loss on each dataset. Here you can see that in the Swedish case, it didn't really matter what we were training on. The loss was still low. And the reason is the way that dataset looks like. There are just very few named entities in there. But in all other cases, you can see that it made a difference whether we were training on the correct language or on another language, in which case the validation loss was always higher. So here is a comparison between the baseline and the federated setup results. The numbers in bold are the best F1 score for each dataset in the federated setup. And in all cases, except for this last Norwegian dataset, we get the best F1 score in a federated setup. But you can also see, for example, from the F1 scores on the Danish dataset, that it made a difference what the dataset composition was. However, all of these results should be taken with a grain of salt because it's just one run. And here you can see, on the left, you can see the aggregated test loss in each of the 3 federated learning settings, S1, S2, S3. And you can see that the model seems to converge nicely. Whereas here on the right, you can see the test loss per dataset in the last federated learning setting where we were training on all 4 datasets. And you can see that there seems to be some competition between datasets. For example, if you look at the purple and the green lines, you can see that as one increases, the other tends to decrease. So, what were our insights? In 3 cases out of 4, the best F1 score was achieved in a federated setup. But we also noticed that federated learning seemed more beneficial for the smaller data sets, so the Swedish and Danish ones. The results are definitely sensitive to data sets composition, as I already mentioned when I showed you the federated learning table, and there seems to be some competition between data sets. One thing we were not expecting but had quite a lot of issues with at the beginning was communication. So just trying to send model parameters back and forth. Because NLP models are generally large. So in the end, we just had to switch to a slightly smaller model to be able to get it to work. And of course, our search has limitations, so we only used one relatively small model, only tried one way of federated learning. And as I said, it was one run per setup, so the results should be taken with a grain of salt. Yes.
And I will conclude with a brief summary. So what we talked about today is that we used federated learning for named entity recognition, where each client it has its own partition in terms of language data for named entity recognition. And there were quite some interesting analysis that we were planning to do that we didn't have time to within the scope of this course. So first of all, we would like to investigate different aggregation strategies and possibility of using federated learning for maybe rare languages, or see how it performs on languages that was not part of the training data among the clients. And while our current setup is scalable, so we can increase the number of clients even further, we would like to investigate scaling it up further while doing this in a truly federated setting where we have actual different devices. And one direction that we might have gone if we had more time is to explore the possibility of integrating the Flower framework with FEDEM. So I see someone shaking their head now, so maybe that's not the best way to go. But it's one option. They have tutorials, so where you can run the Flower client on Fedden. But as we mentioned earlier, we can also do this directly in Flower, so it would be interesting to investigate how difficult that is and how feasible it is for this application. And with that, I want to conclude. So to the corner there, you can see that our teddy bear from the Santa toy factory is now very happy with our federated setup, so he can just chill until Christmas. And thank you for listening.
Any questions?
I have a question. So eventually, did you simulate the process or you deployed it to a cluster? Sorry, maybe I haven't missed the part, but I want to know.
So it was on a cluster, but it was simulated on a cluster. So I mean, what you should do real world is that you start up kind of these processes on different clients, and then you have some server that communicates with those. In our case, we ran it in a simulation, which means that it wasn't different clients, but we kind of simulated it.
So one client on one GPU.
Yeah.
I'd love to hear some of the other aggregation strategies that you thought of, especially, does it make sense that you use the composition of the data set as some sort of like, initial clustering, just because it seems sensitive to the, really sensitive to the data composition. Yeah, sorry.
Yeah, I mean, unfortunately, we didn't have time to investigate it further, but like you saw the kind of the competition between data sets, we wonder if that is something, because what we learned throughout the project was that there is a lot of things you need to think about anew in a federated learning setup. And one of those is kind of this aggregation, because it kind of seemed as though when we did the aggregation, sometimes one data set was kind of benefiting and another one was not. So it would have been interesting if there was some setup to kind of get the best of both worlds. We don't really. Did you have any thoughts on that aggregation?
No, we didn't look into it in detail yet.
Is there perhaps a way to create some sort of custom loss function that has like a constraint on the difference between the dataset losses? So if like it goes above a certain threshold, the difference, it could get extra punished in like the main loss function. So I've had to implement that in some of my projects where I have to balance two states. So it might be something useful.
Yeah, but how do you do that? So you did it centrally, like on the server?
No, I didn't do it federated wise. This is like locally. I don't know how it would implement into federated, but
because I'm thinking like if, for example, if I'm on client 1 and then I want to make sure that I'm not H4 on client 2's dataset, that would mean that I need to communicate the dataset, which I can't. So I suppose it would be something on the server side.
Yeah, it might be way more complicated with federated. Yeah,
that's the general insight. It's way more complicated than federated setup.
Unrelated question to this, you mentioned that you had communication issues with sending the model parameters. Two questions about that. Number one, do you send the full model always?
Yeah.
So you didn't freeze any parameters or something?
It was a full one.
Okay.
We trained a full one.
Have you thought about using low-rank approximations?
You mean like LoRa?
Yes.
No, we didn't do that. So we transferred the whole model. Of course, that could also be done. So you mean that one would essentially transfer the LoRa layers only?
Yes.
That could be interesting. Although I think, I mean, it was an XLM Roberta large that we wanted to transfer. And it's not that big. It wasn't on the size of billions of parameters.
But in terms of gigabytes?
Yeah. I don't know what oh yeah, maybe it's gigabytes. But sure, that could have been interesting to
Because
do.
that's what we tried in the beginning, like our model was like 5 gigabytes and then I got euro 500 on and yeah, so it probably reflects.
Yeah, it was exciting. Yeah, yes, again, federated learning has more complications to it than expected.
Yeah, I have a question.
So suppose so instead of having one large model for named entity recognition, because it crosses some threshold for the model size to be exchanged. So let's say maybe we will have like a collection of smaller models that are highly specialized on specific tasks, like named entity recognition of executives in the C-suite of the Nordic countries, right? Well, of course, the people who will be qualified to actually make sure they are the right entities are those who are in the C-suite, right? So this is, again, I'm going to try to make sure you also put a commercial hat. Say you want to take this idea and start up some kind of a federated product. And your product, essentially, in this case, would serve like the C-suite, right? Because they all kind of use each other's memory to. And of course, with some kind of federated setting, you can, in the spirit of Blue Sky. You guys know about Blue Sky, right? So yeah, it's the Twitter's co-founder that's rebelling against X. So you could actually, in fact, even have a free group in Blue Sky that's like any named entity recognition federation for C-suite Nordics, whatever. So people can join in Blue Sky, they own their data, and then you can essentially give them some kind of a flower thingy that they're part of. So when they work hard to name people, your model trains, but then it only serves others in it. And then you can also do like, you guys know Supernova? It's another social media where they actually share the ad revenues to the people in the network. So I'm just saying these things are already kind of out there. So from what I heard so far, it sounds like this is fairly straightforward to try. But the big constraint in all these settings will be the model size itself that you transmit, right? Because the computation can happen on each device. So let's say, if you were to turn this into some sort of a product, what do you see the main impediments are in terms of riding the social media federation wave and going for niche target markets?
I think we should ask. We thought a lot about this before. Does anybody have an answer top of their mind? But your question is essentially if we were to kind of try to turn this into a product where you can have different people who want to do.
Yeah, exactly, right? Because you can imagine executives in Nordic companies, and it's like, how do you remember everyone, right? That's everyone remembers different subsets in London. That definitely people pay for this, I'm sure. So I'm just saying, it's there. Like, what would be technically, if the model size is small, that's fine, I think. So now, like, what would be the next steps you need? Like, maybe. It's good to think about.
I suppose one first step would be if this is federated learning is kind of its selling point is kind of that you have privacy. So I suppose you would need to show guarantees that you actually provide that level of privacy. I suppose that would be a first step for like showing that you actually have what you are selling. With respect if you're sharing data, not sharing data, but learning some data from different people. Also, I think this is what we saw in this project. Oh, I have no battery, but it should be fine. What we saw in this project is that you kind of need to be a bit careful with like data heterogeneity, as we saw that. To some point you can get good performance, but then when you start to go into the nitty-gritty details, we could see this effect of maybe Danish is not entirely like close enough to Swedish, so then you see this competition, and then I suppose that would need to be handled. Because I suppose we would get even more heterogeneity.
Yeah.
That's what you're describing. So how to kind of make sure that you get all the benefits, but none of the negatives.
No, I think that's a really good example because you can imagine, right? Different corporations will have different number of executives, right? Of course, Apple has more. So it's kind of similar problems. But I will ping you guys later about different models of economic architecting now that's coming out in the new School of Economics. So, for example, those who join the federation will actually be shareholders of your operation, right? Because those who contribute more, any power can also get more. These things are, anyways, parallel.